Unsurprisingly, for these limits of functions of two variables, we have lots and lots of limit laws, properties, whatever you want to call them. I've got a couple pages of notes here just to go through all of these rules. So the following rules hold if L, M, and K are real numbers. So the limit is xy goes to x naught, y naught of f of xy is equal to L. Limit is xy goes to x naught, y naught of g of xy is equal to m. K is going to be a real number that we're going to sometimes multiply by here. So let's just crunch these through one by one. The sum rule, we do the limit is xy goes to x naught, y naught of the sum of f of xy and g of xy. Well, the individual limits here of each of those are L and M. And so the limit of the sum is the sum of the limits. Difference rule, limit is xy goes to x naught, y naught of f of xy minus g of xy. The limit of the difference is unsurprisingly going to be the difference of the limit. So all of these should be very evocative of calculus 1 limit rules in one dimension. Constant multiple rule, if we multiply if we take the limit as xy goes to x naught, y naught of k times f of xy, so we simply multiply our limit by k. Product rule, limit xy goes to x naught, y naught of f times g. So the limit of a product is the product of the limits. Quotient rule, limit as xy goes to x naught, y naught of f of xy divided by g of xy. The limit of a quotient is the quotient of the limits. What's the one thing we need to say here? This holds, let me put a little asterisk here, this holds if m is not equal to 0. So of course, if m is equal to 0, that's the limit of g of xy. Then we can't divide by 0 here. Power rule. Limit is xy goes to x naught, y naught, f of xi raised to the nth power. The limit of the power here is going to be the power of the limit. So L raised to the nth power, we're asterisk down here, blue asterisk, we're assuming n is a positive integer. And then finally a root rule here. We take the limit as xy goes to x naught, y naught of the nth root of f of xy. This is going to be the nth root of L, assuming n is a positive integer again. And if n is even, assume L is positive. Otherwise, like if n is 2 here, we're taking the square root. We don't want to be taking the square root of something negative. So all 7 of these rules here should feel very unsurprising. They're all in the textbook. Let's just maybe do, we'll definitely do more complicated limit rules in the future here. I shouldn't just say limit rules, but limit calculations in the future. Let's start off with a couple of relatively straightforward ones that are kind of achievable using calculus 1 techniques. Later on, we'll go into the limits that really get into what makes things so interesting with multivariable calculus limits here. So this first example, limit xy goes to, oops, I didn't write. My apologies here. That marker is dying. That marker is also, okay, that's doing better. Xy goes to the point 0, 1, that's important. Okay, so limit is xy goes to 0, 1 of x minus xy plus 3 divided by x squared y plus 5xy minus y cubed. Now, we could break this down into lots and lots of limits and say, okay, we're going to use the product rule to do the limit is x times y. We're going to use the sum rule a couple of times in the numerator. We're going to use the product rule a couple times in the denominator, a couple application of power rule, constant multiple rules, quotient rule, and stuff like that. We can do, we could do all of that if we wanted to, but that would take, 10 minutes for me to explain all of that. So let me just kind of say, just like in Calculus 1, as long as everything's nice, and this is a case where everything here is going to be nice, as long as everything's nice, we can simply evaluate this limit by substitution. So what do we do there? Everything is going to be behaving. So if we can plug in, and the reason this all works is that the denominator is not going to equal 0. So, and we plug in x is 0, y is 1. We're substituting in 0 minus 0 times 1 plus 3 over 0 squared times 1 plus 5 times 0 times 1 minus 1 cubed. So importantly, we're not dividing by 0. If we were dividing by 0, this whole approach is out the window. Wait for the videos later in class to see how to handle that. But in this case, 0 minus 0 plus 3 over 0 plus 0 minus 1. So negative 3 is the limit here. One more slightly more interesting problem here. Limit xy goes to 0, 0. X squared minus xy over square root x minus square root y. So now we try to plug in 0, 0. We get 0 upstairs and 0 downstairs. That's not good. So how to handle this? We're going to do a classic Calc 1 trick of square root x minus square root y. Let's rationalize the denominator by multiplying by the conjugate upstairs and downstairs. And then we'll be able to do some algebraic simplification. So we have a square root x minus square root y, so let's multiply this by square root x plus square root y. And what do we end up with here? Limit as xy goes to 0, 0 of... Okay, so this simplifies down to x minus y. That's the whole point of doing this multiplied by the conjugate. X squared minus xy, I can factor out an x from that. Just have x minus y times square root x plus square root y. And at this point, the eagle-eyed among you should realize those factors can cancel out. And so we are left with limit xy goes to 0, 0 of x times square root x plus square root y. And now this is very easy to evaluate. We can just do this with substitution. And in fact, this is just going to be 0 times square root 0 plus square root 0. I think that's 0. Okay, so that was a bunch of limit properties, limit rules to know. A couple easier examples that we could kind of do using Calculus 1 methods. Future videos will be doing the really interesting Calculus 3 multivariable calculus limits.